Hi everyone, my name is Manuel Rigger. I'm a postdoctoral researcher at ETH Zurich in Switzerland, mentored by Professor Ternary. And in this talk, I'm going to present the SQLancer, which is a tool that we developed to automatically find logic bugs in database management systems. Data is eating the world. Thus, it is difficult to exaggerate or overestimate the role that database management systems, or short DBMSs, play within our computing infrastructure and even society. Just to pick a couple of examples, SQLite is an embedded DBMS that is used within all of our mobile phones, operating systems. It's used embedded in many applications, for example, web browsers. And overall, the SQLite developers speculate that there are over 1 trillion SQLite databases that are in active use. As another example, I guess many of you have used or know MySQL, which is the most popular open source DBMS that we tested. Then TiDB and CockroachDB, they are highly popular as well. And they are prime examples of so-called new SQL DBMSs, and they are commercially developed by 2 companies. It is not very surprising that these DBMSs are strictly tested, because even a single bug might affect many users in practice. For example, SQLite has about 700 times as much test code as it has source code. SQLite's test cases achieve 100% branch test coverage, even more so they achieve 100% MCDC coverage, which is even a stricter coverage metric that is used in the domain of safety critical systems. SQLite is also, for example, extensively fast by Google's open source fast project, but also by security researchers. And as a final example, besides more conventional kinds of testing, the SQLite developers also use anomaly testing to even validate that SQLite works correctly in the presence of out-of-memory error situations, input-output errors, and power failures. Despite this, we have found over 450 bugs in these DBMSs, many of which also we found in SQLite. In our work, we aimed to find logic bugs or correctness bugs, which are bugs for which the DBMS returns an incorrect result set. We believe that these kind of bugs are important and difficult to find, given that, for example, for crash bugs, the user gets immediate feedback that something went wrong, but this is not the case for logic bugs where silently an incorrect result is computed. You can see here a test case that demonstrates a logic bug that we have found in SQLite. You can see that first we create a table, then we create an index, which is an auxiliary data structure, and then we insert some values into the table, and finally we issue the query to the DBMS. You can see that the query has a where clause, and the predicate uses this is-not operator, which is a null-safe comparison operator, meaning that even if one of the operands is null, it will still evaluate to a Boolean value. So what's the result set that should be returned? Well, 0 is not 1 should evaluate to true, since these are different values, so it will be part of the result set. Then 1 is not 1 evaluates to false, since these are the same values, but 2 is again part of the result set, and also null, since we are using this null-safe comparison operator. So if you execute a test case using the latest version of SQLite, this is the result that you will get. When we tested SQLite, it was still affected by a bug, which caused it to omit null from the result set. After we reported the bug, it was quickly fixed, and now this works correctly. So how could we find such logic bugs? One potential approach would be differential testing, which was first proposed by Microsoft Research about 20 years ago. And the idea here is that we would generate a SQL test case that is sent to multiple DBMSs, for example, Postgres, MySQL, and SQLite, each of which then returns a result set. And if the result sets are all the same, then they seem to work correctly. But if they differ, then there is at least a bug in one of the systems. So if we execute the test case on Postgres and MySQL, actually what we'll get is a syntax error. And SQLite would return the incorrect results, making it difficult to find this logic bug. Well, why a syntax error? If we look at this table definition, we actually see that we didn't specify a data type, which is not required for SQLite, but it is required for MySQL and Postgres. And also, the is-not operator is not supported in this way in Postgres and MySQL. So Postgres provides an equivalent, is distinct from operator, and MySQL provides a nice-if comparison operator that we could negate. But you can already see from the simple example that things get quite tricky. In general, we found that the common SQL core is rather small because each DBMS provides extensions to the standard or does not strictly follow it. This is also confirmed by companies. For example, Cockroach Labs, they wrote in a blog post that they are unable to use Postgres as an oracle when using differential testing because CockroachDB has slightly different semantics, and generating test cases that execute yielding the same result on both systems is tricky. Thus, we came up with SQLancer, which is a tool to automatically test DBMSs. Actually, SQLancer is available on GitHub, and it should be quite straightforward to get started with it. So you can basically clone the repository, use Maven to build the project since it's written in Java, and then execute a jar specifying which DBMS you want to test and also which oracle to use. SQLancer operates in 3 phases. First, it generates a database, then it generates a query, and finally it validates the query's result. And from that, you can go back to generating a new query. Specifically, SQLancer by default generates 100,000 queries for each database. The reason for this is that generating a database is more costly on many or most systems than generating queries or executing the queries. Or we can go back to generating a new database. And here we typically generate databases with tables that hold up to 30 rows. The reason being that if the databases are smaller, then the queries execute more efficiently. So these 3 phases actually relate to 2 challenges in automatic testing. The first 2 relate to how an effective test case can be generated. And the second and third relate to how a test oracle can be constructed. So a test oracle is a mechanism that validates whether the result is correct or not. So actually, generating a database and generating queries are the perhaps less interesting part. In SQLancer, we manually implemented some database and query generators that heuristically generate statements that are supported by the respective DBMS's SQL dialect. Actually, there exist a number of similar database and query generators that you could use instead. Now, the focus of these talks are test oracles for finding logic bugs, which is also the novel aspect in our work. Specifically, we propose 3 testing approaches, 3 test oracles: pivotal query synthesis, or short PQS, non-optimizing reference engine construction, or short NOREC, and ternary logic partitioning, or short TLB. PQS has allowed us to find and report about 100 bugs, and the idea was to generate a query for which it is guaranteed that a randomly selected row, to which we refer to as the pivot row, is indeed fetched. NOREC allowed us to find and report over 150 bugs, and the idea was to detect optimization bugs specifically by rewriting the query so that it cannot be optimized by the DBMS. And finally, TLB allowed us to find and report over 50 bugs, and there the idea was to partition a given query into multiple partitioning queries, each of which compute a part of the result, and the parts can then be combined to yield the original query's result, which can be validated. So let us start with the first approach, namely PQS, which is also the first approach that we came up with. The idea there was basically to validate the result set based on only one randomly selected row at a time, and we refer to this row as the pivot row. Then the idea is that we generate a query that is guaranteed to at least fetch the pivot row, potentially among other rows in the result set. And as a last step, we check if the pivot row is contained in the result set. If not, a bug has been detected. The steps specifically look as follows. So first, we randomly generate a database. Then we select a pivot row. Actually, a pivot row is one random row that might refer to multiple tables and views, but it's, as I said, only a single row. Then we generate a query that is guaranteed to fetch the pivot row. And here our insight was that we only need to generate predicates that evaluate to true for the pivot row so that we can then use them in join and work clauses, knowing that the pivot row will be part of the result set. So for our example, let's just assume that we randomly generate the predicate that already allows us to detect the bug. And we implemented an expression evaluator for each node. Now, based on this, we can evaluate this tree based on the pivot row, meaning that there are two kinds of leaf nodes. One of them are column references, and for column references, we just return the values from the pivot row, meaning that here we have a reference to C0, so C0 returns here null since this is the value from the pivot row. The other kind of leaf nodes are constant nodes, which return their assigned literal values. So here 1 just returns 1. And compound nodes compute the result based on the children. The is not operator here compares null and 1, and since they are not the same value, the operator returns true. Now, knowing that the predicate is to true, we can now use it directly in our work clause. We could have also used it in any kind of a join clause, knowing that the result will be contained. But what if the expression does not evaluate to true? In this case, we have a fix-up step. So if the predicate evaluates to false, we negate the expression or the expression's result. And if it evaluates to null, we append this additional is null operator. Alternatively, we could also have just checked that the pivot row is expectedly not part of the result set when the predicate evaluates to false or null. And finally, we validate that the pivot row is indeed contained in the result set, for which we use SQL. So you can see here for SQLite, we use the intersect operator that checks whether the pivot row values on the left-hand side are contained in the result that is returned by the query on the right-hand side. So if the result is non-empty, then we have then we can basically validate that we see that the pivot row is part of the result set. We evaluated and implemented the approach for 3 DBMSs, namely SQLite, MySQL, and Postgres. We found about 100 unique bugs, most of which have already been fixed. You can see here that we found most bugs in SQLite, and one significant reason is that we focused our testing efforts in this and also other works on this DBMS, because the SQLite developers were very responsive in fixing fixing the bugs, and typically fixed them even a couple of hours after we reported them. 61 of the bugs that we found were logic bugs. The others were error and crash bugs. So error bugs are basically where the DBMS returned an unexpected error message, for example, that the database was corrupted, and crash bugs are when the process exits with an abnormal execute. So what are the advantages and disadvantages of BQS? First of all, of course, it was a highly effective approach for finding bugs, but it's restricted to mainly testing the implementation of the work clause. So for example, we do not test additional SQL features such as aggregate functions, which are also important and widely used. One advantage of the approach is that it establishes a ground truth, because we implement these expression evaluators that basically are a reference system against which we compare. And we basically could implement these expression evaluators in a very naive way, because we found that the DBMS under the test is the bottleneck in terms of performance and not our testing tool. And finally, implementing the expression evaluators comes at a cost. So first of all, this wouldn't have been possible without some domain knowledge, for which we relied on the SQL dialects documentation, and also the implementation effort is moderate. So even though we could naively implement the operators, we didn't consider implementing, for example, functions like printf, which would have incurred quite some implementation effort. So here we believe that this approach is mostly applicable to testing the core semantics of a DBMS. Now, the second approach that we came up with is NOREC. And with NOREC, we basically wanted to concentrate on an important subcategory of logic bugs, namely optimization bugs, which are logic bugs in the query optimizer that cause the DBMS to return an incorrect result set. So actually a number of the findings of PQS were also such optimization bugs, which motivated us to specifically pursue this. And one goal here was also to basically provide an approach that requires less or no domain knowledge and also less or no, probably less implementation effort. You can see here again a motivating example, namely a test case where unexpectedly SQLite didn't fetch any rows due to a bug in the query optimizer. Specifically, the like optimization malfunctioned. So the like optimization is applied to regular expressions. And in our test case, we used the glob regular expression operator. So this optimization was incorrectly applied, namely to non-text columns and this pattern prefix of minus. Here we also reported this bug and the SQLite developers quickly fixed it, and now SQLite expectedly fetches the row from the table. Now about potential existing approaches that we could use, again, differential testing comes to mind. Because, for example, if we think about compilers like GCC or LVM, they basically provide optimization flags like O3 and O0, basically, which allows us to enable all optimizations or most of them, or disable most of them. And if we would have something like this for DBMSs, then we could first enable all optimizations, potentially triggering this bug in the optimizer, and in which case the incorrect result would be returned. And then again, disabling all optimizations to obtain the correct result. And by comparing the two, we could then spot the bug. So if we look for the options that, for example, SQLite provides, then we actually quickly realize that no such option to disable all optimizations exists. Perhaps the most related one is the one to control whether the like operator should be case sensitive or not, but this actually doesn't help us to find the bug. And in general, we found that most DBMSs provide only very limited control over optimizations. So the idea in this work was that we wanted to rewrite a given query that is optimized by the DBMS so that the DBMS can no longer optimize it. So basically, instead of relying on the DBMS to provide an option, we wanted to rewrite a query ourselves to disable optimizations. Basically, the approach would look as follows. We first generate an optimized query that potentially triggers the bug in your query optimizer. And then we would have this translation step that derives an unoptimized query that does not trigger the bug in the query optimizer. And by comparing the two result sets, we can then expose the bug. So let us assume a specific format, a concrete format for the optimized query, namely that we select all records from this table T0. Actually, the approach would also work for multiple tables where the predicate phi here relates to true. And in our motivated example, the phi corresponds to the regular expression. There is actually very unclear how we could derive an unoptimized query from this kind of optimized query format. And to this end, we basically had two insights. First, the predicate phi must always evaluate to the same value, no matter where exactly in the query it is used. So this means now we can take the phi predicate from the where clause and move it directly next to the select statement. And what's the effect now of this query? Well, the predicate is evaluated on every row or the cross product of every rows from the tables. And the result set will consist of either true and false values. So true if the predicate evaluated to true and false otherwise. Since in our example, T0 only holds a single row, we get back only a single value. And you can see that this is true. And what can we learn from this? Well, first of all, from the optimized query, we can learn that phi evaluated to true for one row because one row is contained in the result set. So here we count the number of rows. And for the unoptimized query, we can learn that phi evaluated to true for one row because one true value is contained in the result set. So here we count the number of true values in the result set. And this should correspond. The second insight is that DBMSs focus their optimizations on reducing the amount of data that is processed. So for our example, this mainly means that the where clause is optimized because it controls which data is fetched. And for SQLite, this actually triggers the query optimizer to use an index, which is this auxiliary data structure that makes query processing faster. But for the unoptimized query, since the predicate needs to be evaluated on every row anyway, SQLite decided to just scan through the table. Now, taking these two insights together, actually what happens when we send the optimized query to the DBMS, then we trigger, or we are likely to trigger the bug in the query optimizer. So here in this example, we get back the empty result set. But if we send the unoptimized query to SQLite, it doesn't trigger the bug in the query optimizer, and we get back a single true value for this example here. And from the true value, we can infer that the optimized query's result should have contained one row. This was not the case and allowed us to find and report this bug. Implementation-wise, we can actually make use of aggregate functions that SQL provides. So for the optimized query, we can use the count aggregate function to count the number of records in the result set. And for the unoptimized query, we can use sum to sum up how often phi evaluates to true, in which case it is implicitly cast to 1 here for SQLite. And then basically we get back a single integer that we can conveniently compare to implement this technique. We evaluated this approach on 4 DBMSs, namely SQLite, MariaDB, Postgres, and CockroachDB. And overall, we found more than 60 bugs, most of which have already been fixed. Overall, about 1/3 of these were optimization bugs. So we found more error and crash bugs, suggesting that these might be more common or easier to find. So how does NOREC compare with PQS? Well, first of all, it is still restricted to finding bugs in the implementation of work clauses, just like PQS. Now, different to PQS, NOREC doesn't establish a ground truth. It is basically a metamorphic testing approach where the idea is that we have an input to a system and its output, and from this we derive a new input that is known to have a specific output. So basically, this means for us that we only expose inconsistencies in the DBMS under test, but if the DBMS inconsistently returns an incorrect answer, then we cannot detect it. Now, one main advantage that we want to tackle in PQS is that NOREC doesn't require any domain knowledge, and also the implementation effort is very low since we do not need to implement these expression evaluators. But as I said, it can only detect a subcategory of logic bugs, namely optimization bugs. So let us continue with the last and latest approach, TLB. The idea was here, or what we wanted to tackle was that NOREC is mostly limited to testing work clauses, and we wanted to test a wider range of different SQL features, for example, aggregate functions. So the core idea then was that we basically had an original query that we generated, and from this we wanted to derive multiple so-called partitioning queries, each of which computes a part, and the individual parts can then be combined to yield the original query's results, which can be validated. So to illustrate this, you can see here that we basically would generate a query Q, which denotes the original query. You can also see here that we use this circle to denote the query's result set here, the original queries. And then we partition the result set by deriving multiple queries from Q. And by composing these results of the partitioning queries, we gain now a new result set. And the assumption is that this result set is the same as the original queries. If they are, then everything seems to work correctly, and otherwise we have found a bug in the system. So for terminology, these queries that we derive from the original query are called the partitioning queries, each of which computes a partition. And this diamond operator here is called the composition operator, which combines or composes the partitions to obtain the new result set. Now, I guess while the general idea sounds plausible, from this we can actually still not obtain a concrete test oracle. So the challenge is still to find a partitioning strategy that is valid and which also stresses the DBMS in different ways so that we can expose bugs in it. Now, in order to realize this technique, we had the following insight. Consider that we have again a predicate phi and a given row, then exactly one of the following must hold. Phi evaluates to true, not phi evaluates to true, meaning that phi evaluates to false, and phi is null evaluates to true, meaning that phi evaluates to null, since SQL is based on a ternary Boolean logic. Now, based on any kind of given records or result set, we can basically take it and partition it into three parts, namely for those where the predicate evaluates to true, for where it evaluates to false, and where it evaluates to null. We refer to these three predicates as the ternary predicate variants. And here you can see a test case that we found, or that exposed a bug in MySQL that we found using this technique. Namely, this query here is supposed to fetch the cross products of all records from T0 and T1, where the column here evaluates to the same value. Now, unexpectedly, MySQL didn't fetch any rows, even though the comparison between 0 and -0 should yield true. How do we define this bug using TLB? Well, we first generated this original query that simply fetches the cross product of all values from T0 and T1. Now, this query is expected to not trigger any bugs in MySQL and also hopefully not in other DBMSs. And indeed, MySQL fetched the correct result. And from this we derived more complex partitioning queries. You can see here that as phi, we basically generated a comparison between the column C0 in T0 and T1. And these three queries here unexpectedly didn't fetch any rows, which allowed us to finally report this bug because we expected that it would be the same as for the original query. So basically what we did is we took now this general idea of query partitioning and we instantiated it with the more concrete idea of ternary logic partitioning, where basically Q was the original query that simply fetches the cross product of all records from T0 and T1. Then we had the partitioning queries with the non-negated version of the predicate, the negated version of the predicate, and the null version of the predicate. And as a composition operator, we used union all, which combines the records without filtering out duplicate rows. So let us look at this in a more structured way. Namely, you can see here when we want to test where clauses, that basically the format for the original query, which you can see in the first column, the format of the partitioning queries in the second column. So this is instantiated 3 times with the non-negated, negated, and is null version of the predicate. And in the third column, you see the implementation of the composition operator. So this symbol here basically is the multi-set addition, and in our case, this means union all. But initially, I promised that we came up with this approach, or we wanted to tackle that the existing approaches were only allowed us to test where clauses. So this approach is can test a wider variety of features, and I want to give you one example, namely for aggregate functions. You can see here again the format of the original query and the partitioning query, which looks quite similar as the ones before. More interestingly here is the composition operator. So a partition in this context is an intermediate result, the maximum value that has been computed so far, rather than a subset of the original result set, which was the case for the word test oracle, for example. You can also see here that in the composition operator, we use this max aggregate function and in the partitioning queries. So we basically have 2 applications of it. I want to show this on a concrete example of a bug that we found in CockroachDB. So basically, if we send this max aggregate function query to CockroachDB, it returned null. And from this, we derived the partitioning queries where you can see that in the partitioning queries, we use the max aggregate function, and then again in the outer query, which implements the composition operator. And here, CockroachDB returned a single value, a single record with the value 0, which allowed us to finally report this bug because it didn't match the original query's result. So what I've shown on the previous slide is an example of a so-called self-decomposable aggregate function. There is a more general category of decomposable aggregate functions. I don't want to provide a definition here, but I think it gets clear on a concrete example. Namely, if we want to test the average aggregate function, then it quickly becomes clear that a single value in the partition doesn't suffice to reconstruct the overall average value, because the average value in the partitions might be computed based on a different number of rows. Now, in order to keep track of this, actually the result of a partition is both the sum and the count, so that we can recompute the overall average at the end. So we implemented this approach for a number of systems and overall found close to 200 unique previously unknown bugs. And again, many of these have already been fixed. In terms of test oracles, the were oracle is the simplest test oracle that we came up with as part of this approach, but it actually turned out to still be the most effective one. The other test oracles, they found a number of interesting bugs, but fewer overall. But one thing to note here is that we only tested these more advanced test oracles for DBMSs for which the TLB were oracle could not find any additional bugs, because basically these more advanced oracles can also find bugs in the implementation of the were clause, but they generate more complex test cases by doing so. And it's more desirable to thus first use the TLB were oracle to find these bugs. Now, what are the advantages and disadvantages? So with TLB, we now support testing a wider range of features, for example, aggregate functions. But TLB is still a metamorphic testing approach, meaning that the domain knowledge, the node domain knowledge is required, and also that the implementation effort is low. But similar to NoRec, we can also not establish a ground truth. So how would you use our approaches in practice? Probably one useful strategy would be to first use NoRec, first use and implement NoRec to quickly find the optimization bugs, which seem to be very important. Then use TLB to test a wider range of features, for example, aggregate functions. And finally, use BQS, which incurs more implementation effort, but allows to more comprehensively test the DBMS. SQLancer and our approaches have been already widely adopted in practice. I want to pick a couple of examples. Namely, DuckDB runs SQLancer now on every pull request as part of its continuous integration process on GitHub. Then Ilya from Yandex contributed a ClickHouse implementation of TLB specifically to SQLancer, which they use to test their DBMS. Then MongoDB recently published a blog post where they state that they have been able to identify over 100 potential problems using SQLancer, which they adapted to test their DBMS. Then PingCap implemented Go SQLancer, which is a Go version of the approaches that they implemented to test their DBMS TiDB. And as a final example, Natsli from Cytos Data implemented support for Cytos, which is in a Postgres extension. And she also wrote a very excellent blog post about TLB and the experiences that she made with SQLancer and implementing the TLB approach. So please also check this one out. And with that, I want to wrap up. I have presented that the goal in this line of work has been to detect logic bugs in DBMSs. We came up with BQS, where the idea was to validate that the DBMS works correctly on a single randomly selected row called the pivot row. The second approach was a metamorphic one, namely NoRec, where the idea was to derive an unoptimized query from a given optimize query and then compare the results, which allows exposing optimization bugs. And the latest approach that we came up with is TLB, which is also a metamorphic testing approach, and where the idea was to partition a given result set into multiple parts by using partitioning queries and then combining the individual result sets so that the original query's result can be obtained. And overall, using this, we have found over 450 bugs in popular and widely used DBMSs, demonstrating that the approaches are generally and highly effective, and actually a number of other people also found bugs using the approaches in SQLancer. With that, thanks a lot for listening, and I'm very much looking forward to questions and discussions. Thank you.